So, uh, welcome back to this third day. So we will do some. Uh, First, we will in the next in the previous day's lecture. There is a wrong in question number 5. So first we actually rectify the problem, and we will do some work that that I want to demonstrate in this session. So let's start with the first today's first assignment, that is question number 5 that we did in the uh, previous lecture, that should be rectified. So let me share my window. I think I am audible and my screen is visible. If not, please tell me. Okay. Oh, okay. So let's start. So in the assignment 2, sorry. Question number 5, if you look, the question was for a free particle state, the quantities that show time dependence on the following are A helix, B helix square, C L square, D X. So one hints also given is that the time derivative of expectation of a operator A can be written as expectation of commutator H and A. Now if H and A commutes, then there will not be any time dependence. The slides are not visible, no? Is it visible, slides? 1 minute. Now I think it's visible. any time dependence. Okay, so what we so we know that H and Lx commutes, so it will not show any time dependence. Now let's do a quick mathematics on that. So we can think that it is Lx dot Lx. So if we use, well, it will be like something. So this is also, if this term is 0, this term is 0, then it will also be 0. So please rectify. This will not show any time dependence. This will not show any time dependence. Now now if we do for H L square, so L square is nothing but Lx square, Ly square and Lz square. So if you see the expression of H, it will be T plus V. So it is the T is kinetic energy part and V is the potential energy part. Now T kinetic energy part is also incorporated by translation kinetic energy and angular. So this angular part is nothing but L square. So it's already had L square in its term, therefore all therefore this L square H term, that will be also 0. That means this is also time independent. This will not show any time dependence. But as we know, this term will not be 0 because this because if you see that the translation kinetic energy, that is a, so it can be written as H cut by 2m del x by del x square x, that is also not 0. So and angular part will not be 0. Therefore only this term is so will show the time dependence. So this is the thing that I want to say for the last day lecture. Now if you have any question you can ask, or otherwise I will go to the next day lectures. So let's look at what is the thing we had in this week assignment. So in week 2 the lecture has been started with coupled with this function phi, or incorporated with two-state problem so this is a two-state problem 1 and 2 with corresponding energy E2 E1. Now applying some time dependent perturbation. By the way, these both coefficient are time dependent. Okay, so this is a time dependent perturbation applied. Okay, so total Hamiltonian becomes previous Hamiltonian without perturbation but with perturbation term. So with perturbation it is something, sorry, without perturbation this is the energy of the two state. Now with perturbation it becomes so this is your time dependent linear equation. Now Now if we take a time derivative, yes, A1 or A2 is the coefficient of the state. Okay, so if I say let's do something else. Okay, so suppose it is a Hamiltonian acting on psi, you will get energy of psi n. Okay, so psi n forms complete basis where n can be 1, 2, 3 up to infinity. Okay, now if psi n is complete basis, suppose then that means psi 1, psi 2 dot psi n dot to infinity are basis function. Now then you can write a arbitrary wave function as a linear combination of your basis function. Okay, so now for a two state system, so your basis function is 1 and 2, then how you can write it? You can write these things as a linear combination of two state, n is equal to 1 to 2, an n. Now when n is equal to 1, that will be 1 1. Okay, for a now if for time dependent thing, you can add I E n t h cut t by h cut, then you can write it like this. Sorry, for 2 it will be the something like that. This is the corresponding energy E2, sorry, E1 corresponding energy of E2. So these are the coefficient which are time dependent coefficient. Okay, and square of this implies the probability. Okay, a1t square plus a2t square, like this, a total probability. So this is probability of state 1. Okay, and this is the total probability okay of, if I say it says, if I denote it as psi t, then it will be total probability of wave function psi t corresponding to wave function psi t. Okay, how this is yes, it is equal to 1 if there is no other, is two level system, this value must be 1. Okay, but if you want to say what is the probability of 1 at a time and what is the probability of 2 at a time, then they should not be 1. Okay, so individually a1 square may be or may not be 1, but a total probability in the system is 1. Okay, we will look at it in the next with the progress of the assignment. Okay, so let's, so if we do this little bit more or mathematics, we will get this thing. Let me use this t, then it will be more E1 th cut. Similarly A1t into minus ai E1 by h cut e th cut, and there should be 1 plus a2t dot 2 plus a2t Similarly, if you put h0 with this, you will get a a1 t u1 1 h cut plus this one h0 with this, then we will get a2 e2 now if we incorporate with this, then this will give you okay, let me go to this. Then we will get a1t ei So if we multiply with 1, then what we will get? So if we multiply with 1, then this term will be come out, and 1 and 1 is they are orthonormal, so this will be 0. So we will get e1t dot ei1t by h cut plus, and this I and I square that is plus, and h cut will be cancel out. That will be a1t e1 1 h cut. On the other hand, so 1 h bar t 1 plus a2t so this value is 0. Therefore, if you have applied a perturbation in state 1, and if it not do anything, if the system is still in one state, therefore this doesn't mean anything, so this result is 0. So what we will get a1t this value is 0. Oh sorry, there should be one more term here from this one. That will be a1 t e1 e. So these two will be cancelled out. So what will be left over, and there will be IH cut. You A2T therefore U1T can be written as if we take E2 minus E1 is H cut omega to 1, then U1T can be written as A2T by H cut EI omega to 1T 1 H bar similarly E2T so this is some coupled differential equation. So coefficient of A1 is dependent on coefficient of 2. Similarly, coefficient of state 2 is dependent on coefficient of 1. So last lecture I have shown you how to make it coupled differential equation to only single differential equation, and that can be used to determine to solve other things in week 3 that you can watch. And now using this equation today we will start doing our week 2 assignment solution. Okay, so let's start. So we will use this equation and we will see how we can incorporate in our assignment. So now the question number 1 of week so give question number 1 is asked given the Schrodinger equation responding to the Hamiltonian is the correct answer statements is or are. 1. The value of n not be infinite. 2. Energies can also have imaginary values. Functions psi n from an orthonormal set. For any so as I mentioned previously, so if unperturbed Hamiltonian yields the energy term this one, then psi n forms complete basis, and n can be anything, any integer number to infinity. Okay, think as a case of particle in a one dimensional box. Therefore this n cannot be infinite. This is incorrect. Okay, now similarly this en is a measurable, can measure it, measurable quantity, so that must be real, and H0 is a Hermitian operator. Therefore eigenvalues of Hermitian operator always real, so it cannot be imaginary function value. Now psi n from a orthonormal set. So what is the orthonormality property? If you set two state problem, then your basis is psi 1 and psi 2. Now the phi part is, you can say as C1 psi 1, C2 psi 2. So now what they says, this if psi 1 and psi 2 that is 1. So this is called normalization property. But on the other hand, C1 psi 2 psi 1 is always 0. So this is orthogonal property. So therefore this kind of relationship can be written as psi j psi I psi j is a Kronecker delta. Sorry. Delta. That implies if I is equal to j, this delta ij will be 1, and I not equal to j, delta I is equal to 0. So therefore, the simple example you can take, particularly in 1D box, you can see the psi 1 and psi 1, all the wave function are normalized. But if you take the overlap between psi 1 and psi 2, there the value will be 0. So they are orthogonal to each other. So if you say the particle in a box, the Hamiltonian actually produce the complete set, psi 1, psi 2, whatever the complete set, then psi 1 and psi 2 are orthogonal to each other, but psi 1 and psi 1 will give you value of 1, normalized. So function psi n, if coming from the unperturbed Hamiltonian H0 psi 1 H0 psi 0 psi n, then this psi n will form a orthonormal set. So this statement is correct. Now as I say that, if you may look at it carefully, if it form a complete basis, then you can write it's a linear combination of two wave function. So linear combination is either plus or minus. Okay, so C1 psi 1 minus C2 psi 2, that is also another function, and that is also another arbitrary function. So if or this is for complete basis also. So like for particle in one dimensional world, again take this problem. So you know the psi 1 psi 2, these are the labels, and if you take the linear combination of these states, you will get another wave function, and the wave function you can expressed as a linear combination of these all states. Okay, now so this statement is also correct. Having said that, let's look at the second question. Okay, if H0 commutes with HT. Now remember question number 5 that we solved few minutes ago. Then there will be no time dependence. So this is cannot be possible. Now both H0 and HT are Hermitian. H0 is Hermitian, we know, because we can measure the energy, but HT is also an Hermitian, because we can see HT is also a Hermitian. In that way you can think like that. It produces a real value. If a molecule HT, what it denotes is in the course of lecture you will say the HT is something is connected to the your selection rule. Okay, so that will provide a real value. Whether it excites or not, there will be no imaginary quantity. So therefore H0 and HT are both Hermitian. And if H0 and HT both are Hermitian, then these cross arguments are not valid. So this is a easy question to address. For a two-level system experiencing a time-dependent perturbation T, the state of the system is given by the linear combination of the two state 1T psi 1 ei h cut a2T psi 2 h cut. The correct statement among the following is or are: coefficient A1 and A2 are in phase with respect to each other. B, the probability of finding a system in state psi 1 is given by C, coefficient A1T and A2T can be obtained by solving the 1 and A2 0 is 0 and 1t is 0 and 2t is 1, it can be concluded that system underwent transition from psi 1 to psi 2. Okay, so let's as previously I said that we will use this coupled differential equation in this lecture. So if I remember correctly, this is the expression A2t I think this is the equation I have written in the few slides back. So I think this is the, yeah, U1t. So where is the phase? This is the phase vector. So this is the phase vector. So phase vector. So you can see these two are, one is minus, one is plus. So both are kind of out of phase. So if A1 oscillate like this, then A2 will oscillate like that. So both A1 and A2 are out of phase. It can be expressed by some other way also. Let me look at it. So anyway, that much is enough. So you can take this is A2t and this is A1t. So they are both are, so A1t or A2t are out of phase. So this is a incorrect. Now probability of finding system psi 1 is given by A1t square. So this is correct. I describe it. We have a discussion about it. So this option is correct one. Now the coefficient A1 and A2 can be obtained by solving TDAC. So I show it in the beginning of the class. You can derive the A1 and A2 from the expression of A1 and A2 from solving the time dependent perturbation theory. Now a1 0, so at it is say time t is equal to 0, so a1 t is 1, a2 0 is 0, and time t is equal to something t dash or t, time t is equal to t we represent, then at is 0, a2 is 1. So therefore the probability of finding here at level 1, so these are two level system, so probability of finding system at state 1 at t0 is maxima, that is 1, and similarly at t0, that means initial condition, the finding of system at level 2 is 0. Now on going t0 to t dash t, the population is reversed, because as we know the probability is proportional to the population. Okay, so if the population reversed, that means the molecule the system has been excited from a1 to t upon shining light or any perturbation. Okay, so therefore this statement is also correct. Now moving to question number 4. Interaction of light with two level system as described in question 1 leads to an atom with a ground state and excited state. Okay, number 1, an atom with ground state and excited state leads to a periodic exchange of energy between the light field and the two level system. Such oscillation are called harmonic oscillation, B periodic oscillation, C Rabi oscillation, and D damped oscillation. So if we look at the expression of A1 and A2 from the expression of uncoupled double differential that I showed it last week, that is A1 dot A1 dot star a1 t I omega 21 a dot t and a2 double dot is minus b star a2 t plus omega 21. Now if you solve this equation, what will be the value of the a1 and a2? That is, you can write this kind of equation is very familiar for solving the double differential equation. Now if we impose the condition is like at t0 the population of a0 is 1 and a2 0 is 0. Similarly at t time the population the coefficient of this thing is state 1 is 0 and state 1 is maximum. Now if we incorporate these two values in that equation, then the expression, and if you use that if we present e to the power I and this thing, the phase factor, as 1 by omega 1 square 4 square half, then what we will get, the expression of a1t is something like this: cos omega t plus omega 21 2 pi sin pi t e to the power it can be done. It's a quick mathematics. So if you use some time, it will get it. You will get the value. So now if you take the square of it, then you will get the probability. So probability of state 1 is nothing but 1 minus 4 v square I am just writing the final form. Okay, now this is P1, this is P2 with respect to T. So now if we plot, so what you can see that P1t is 1 minus P2t. Okay, so if we plot it as a function of time, and population is 0 and 1, so what we will get, if the population of one state while decreasing like this, the population of two state number 2 will increase. So this is state 1. this is state 2. So this kind of thing, this kind of oscillation actually introduced by Professor Rabi. So on his honor is known as Rabi oscillation. So while the probability at P1 state is state 1 is going down, the population of P2 state 2 is rising up. So this kind of oscillation is known as Rabi's kind of oscillation. That can only found when the two wave function, the two coefficient or wave function are out of phase. That is the basic and foremost criteria for getting this kind of oscillation. So if two functions are out of phase, it is possible to see the Rabi oscillation in between them. The phase difference between two waves y1 a sine omega t by pi by 6 and is pi by 3 pi by 6 pi. Okay, this is kind of class 10 or 11 mathematics, but this is important for this course to understand what is the phase difference meaning by seeing there's a wave function. So what we can know that here is just sine theta is sine 90 degree minus theta cos 90 degree minus theta. So y1 can be written as psi omega t pi by 6. So a cos pi by 2 minus omega t minus pi by 6. So that will be cos 3 pi by 3 minus omega t. Now so this will be plus. Now we know cos minus theta is equal to cos theta. Okay, so if we take cos common, then it will be omega t minus pi by 3. So if we compare 1 and 2, oh shit. I will write it again. Okay, so we get y1 is okay, this is also gone. y1 is a cos omega t minus pi by 3, where y2 is a cos omega t. Then y1 and y2 are out of phase by pi by 3. So the phase difference between the two waves, y1 a sin omega t pi by 6 and y2 a cos omega t, is a pi by 3, b pi by 6, c pi, and d pi by 2. The correct answer is pi by 3. Now now question number 6. The wave function of a system is given by psi a n e I e n t h bar psi n under the influence of TD perturbation is HT. The equation IH cut ANT EIEN T by H cut psi m psi n ANT psi m H bar T, sorry, H cut H dash T EIEN T H cut. The correct statement, sorry, correct condition used for the evaluation are: A, psi m psi n 0 for m to n, and psi m psi n is 1 for m not equal to n. B, psi m psi n is 0 for m not equal to n, and psi m and psi n is 1 for all m is equal to n. C, psi m h t psi n 0 for m equal to n, and psi m h dash psi n equal to non-zero for m not equal to n. D, psi m h dash psi n 0 for m n, and psi n is equal to 0 for m is equal to n. Now, to function, two basis set psi m and psi n. So as I mentioned above, they should be psi m and psi n. Psi m and psi n are orthogonal. Then psi m psi n will be 0 when m not equal to n, and psi m psi n will be 1 when m is equal to n. So let's find that option. So first option is saying m is equal to n, that the overlap between psi m and psi n will be 0. So this is a not incorrect option. Second option, psi m and psi n is 0 for m not equal to n, correct, and for m equal to n it is 1. So this option is correct one. And now third one. So as we mentioned previously, if time dependent perturbation leads to you in a same state, then this value will be 0, and this value will be not equal to 0 if it goes to the another state. So the correct option is the third one is 0 when m is equal to n, yes, and psi m is non-zero when m not equal to n. So third option is correct one, and alternatively the psi m, the fourth option is also incorrect. Okay. Now question number 7. The wave function of the system is given by for there is a n level of system and initial state is I, and there is n minus I excited state. You can say that if we denote ground state is a I state, then n minus I is the number of excited state left. So F is represent one of the excited state. Now in a weak perturbation limit, so if we you can think again, it's like a I to F transition is a n number of system. You can take as a second thing as a two level of system. So all the population at weak perturbation limit will be on state 1. It should not, it's that the perturbation is not so high that it can transfer the population. Actually population is nothing but the square modulus of square of coefficient. So the population is only so you can write at A1t is all A1 AIT is 1, and other things except I is 0. So your first option however is not incorrect, but the second option is proposes the correct one. Now again what we can see, it's a the last two option is a, it should be looks like a coupled differential equation, first order coupled differential equation. So if it is first order coupled differential equation, then f and the time derivative of f a should be depend on the ai. So you can see the first option is correct. So sorry, not first option, this option C is the correct equation. Okay, but in fourth option, first of all the H term is missing. It may be the printing mistake, but thing is that H term is missing. But see in the here the time derivative of final state is showing that it is dependent on the coefficient of state F, final state, so which is incorrect. Okay, therefore the only these two options are correct and A and D option are incorrect. Now moving to question number 8. For a transition between an initial state psi 1 to a final state psi f, the influence of time dependent perturbation HT, the correct statements are AIT is 1 indicates 100% population in the initial now psi f star ht psi I t tau not equal to 0, c psi f star ht psi I is 0, d probability of transition from psi 1 to psi f is given by square. Now if coefficient is 1, then the population I have said repeatedly that population is dependent on the probability of the state. So the whole molecule is 1, then 100% population should be in initial state. So first option is correct. Now psi star f psi ht psi I, so it should be non-zero, otherwise there should, if I is not equal to f, then it's always non-zero quantity, otherwise there is no mean of having a perturbation or excitation. Now so this equation, this here we don't need. Now probability of transition from psi I to psi f is given by AFT square. Now it is written as under the so if we write is like this. Okay, so let's take psi I is a linear combination of AI psi I. Now a function using, if we do some time dependent Schrodinger equation, if we solve that this part I h cut dt phi is h phi, where your h is unperturbed Hamiltonian with some perturbed Hamiltonian. I am just writing the final part. So am is denoted by I h cut some integral of a n not equal to m. If n equal to m, the whole integral will vanish, because if n equal to m, this part will not exist. Okay, now let's say n is equal to I for the question, and m is represented as f. So at weak perturbation limit at t0 or at t0 then what we can say, ai at 0 is 1, the other hand ai of 0 is 0. Now at time t, the expression of, now we can write as I h cut n. So one thing is that this I and f is there, and for that is only valid when n is equal to I. Okay, so we can write is t e I omega I f t f h cut t n. Okay, now what I said previously, first a1t is 1, so this can be written as e I f t f h dash I, this is I. Now what will be the probability? Then probability will be, so this is the probability of transition. So question and option 4 is correct, and the expression should be as there is modulus will be t f h cut t I dt square. So this is the probability of transition. So this part will say transition is possible or not. It's possible or not. So that actually eventually leads to selection rule. So the main motto in upcoming lectures is derive the h dash t. What will be the expression of h dash t? So if time permits, we will have a quick overview on how about the expression of h dash t. Okay, so now the option 4 is correct. So let's the second last. Okay, now at question number 9, the wave function of a system is given by psi x of psi 1x 1 by 4 psi 2x plus 3 by 3 root I by 2 psi 3x, where psi 1x, psi 2 and psi 3 are orthonormal with eigenvalues e1, 3e1 and 7e1 respectively. The most probable eigenvalue number of is d is 44 by network connection. Hello. Hello. Okay. So don't know what happened. Should be able to join. Wait, I think there is some issue. I don't know. I have some issue while joining. Wait for a minute. Maybe there is some network fluctuation. Hmm. Yes. Hmm. Okay, now okay. So it's an example of So this is something is a known as this kind of problem is addressed in some phenomena known as Schrodinger cat experiment. So you can think if you take a cat in a box, it is poisoned by some poisonous things, and before it, if you close this box and if you think now if you guess what will be the situation of the cat after some time, so you can guess it is a possibility of the cat is alive or not, is dead or not. So before the measurement you can write the you can think the possibility is a combination of date and possibility of cat condition is a combination of dead and alive. Similarly, if a wave function is a superposition of bases, then when you do the experiment, means when you do the measurement of the wave function, it will be collapsed to a that wave function which has a maximum probability. So in between these three wave function, which one will have maximum probability, that will correspond to the highest probable value, large number of measurement. So to begin with that problem, as I said first first day, the before doing if you see a wave function, if it not normalized, then the first assignment is to normalize the wave function, then judge what will be the other outcomes. So if you have a wave function, now it should be normalized. So I have added as a C or n as a normalization constant. So Cx psi x should be 1. So at this, now one condition is imposed in this equation, that psi 1, psi 2, psi 3 are orthonormal. Therefore if you take psi 1, psi 1, psi 2, psi 2, sorry, phi 2, phi 2, phi 3, phi 3 will be 1. On the other hand, phi 3, phi 1, phi 3, phi 2, phi 2, phi 1 will be 0. So if we project, if we take the normalization, so normalization constant is square. Now this what we will get, I, so we can write it as a integral half of psi star x 1/4 of psi 2x plus, now this term का conjugate 3 minus 2y, so I का conjugate is minus I conjugate psi 3 star x. Now this whole thing is multiplied with half of psi x plus 1/4 of psi 2x plus 3 plus root 2i of 2 psi 3x. That should be equal to 1. Now using this orthonormal property, what we will get, n square is equal to this term with this term. So what we will get, 1/4. This term with this term, other cross term will be 0, 1/16. And now this term with this term, so 3 minus 2y into 3 plus 2y root 2i, that equal to 1. Now with this, what will be the value? So n square 1 by 4 plus 1 by 16, 9 plus 2I square, so 4 plus 2 by 4 is equal to 1. So that will be the 1 by 4 plus 1 by 16 plus 11 by 4. So this value will yield to 16 plus 1 plus 44. So n square is equal to 4 by 7. Okay. So normalization constant is 4 by 7. So psi can be written as 4 by 7 half phi 1x 1 by 4 phi 2x 2 by I phi 3x. So as a total it will be 2 by 7 of psi 1x, 1 by 7 of phi 2x, and 6 plus root 2 root 2 I up to phi 3x. So this is the normalized wave function. So normalization is done. Now what we need, we have to get the coefficient of each state, probability of each state, because when we measure, the system will be false on on 3 different states. Now which has a maximum probability, that will find to be large number. Okay. So coefficient square is nothing but a probability. So for state 1 or 1 and experiment phi 1, the probability will be 4 by 7, 4 by 49. State 2, probability is 1 by 49. State 3, 6 c square minus 2 root 2 I square by, sorry, this will be 7. 49. So 36 plus 8, so 44 by 9. So P3 is greater than P1 greater than P2. So if you measure, then P3 means phi 3 will come at larger number. So those states have a eigenvalue eigenvalue corresponding to psi 3, that is phi 3, that is 7e1, will give you the maximum probability. So correct option is 7e1. Now moving to the last question of the session. The correct statements about relation between vector potential and electric field vector vector E and magnetic field vector B are a electric field E is time derivative of vector potential A B electric field E and vector potential are in phase with respect to each other along the same direction. C. Magnetic field B and vector potential are perpendicular to each other. D. In Coulomb gauge E dA dt. Now, as we said that I will discuss something about the what will be the what does it mean. So this is a this thing is a time dependent perturbation. So how we provide a time dependent perturbation using electromagnetic field. So electromagnetic light is an electromagnetic field, and electromagnetic field has an electric part and a magnetic part. But this is both are the field. So electric field can be have 3 component. Similarly, magnetic part also has 3 components. So total 6 variable. But we have to use this field to a potential in a Hamiltonian. So if we define this this whole thing as a scalar and vector, scalar potential and a vector potential A. So that will be have Ax, Ay and Az. Okay, now we will come to 4 variable. So we convert 6 variable to 4 variable. So there should be a redundancy because there will be infinite probability from going from 6 to 4. So to get 6 to 4 there should be some fixation. Okay, that fixation has been done by Coulomb, and in electrodynamics this kind of fixation are known as gauge, Coulomb gauge fixation. So it can be written as delta E, hello. Yes. Four comp. Yes. Scalar part. Scalar. Okay. So we are converting 6 to 4. So 6 to 4 is a multiple possibility. So just we need to fix it using some gauge, so Coulomb gauge equation. Okay, which is written like this. Okay. Now in Coulomb gauge there is another term of scalar potential is remains 0, and if del dot A is also taken care of 0. Okay, so now this option, this is will be minus del A by del T under Coulomb gauge fixation, and this is something like this. Okay, so your option 4, for now we can say this is an incorrect option. It should be 0. Okay, now let's go by one. Electric field E is a time derivative of a vector potential A. That is correct. From here we can say that this is from these two is a time derivative of the potential, vector potential A. Now electric field and vector potential A are in phase with respect to each other along the same direction. So same direction thing, because it's same direction thing is can be, it is okay, but they are in phase or out of phase, that is needs to be judged. So A is what I say, A is a scalar potential, vector potential. In wave plane wave equation, it can be written as A0 with unit vector of electric field, and it can be written as I k dot r minus omega t plus E, sorry, this is like this, k dot r. Okay, now if you make it, expand it, you can think E I theta plus E minus I theta, it will be give you some quantity of cos theta. Now if you take a time derivative of that, then what we will get, minus I omega and this will give you plus I omega. So the value would be A0 I omega E I k dot r omega t minus E I. Now E I theta minus e to the power minus I theta, so that is, if you expand it, it will be a sine function. So if sine and if so this scalar vector potential is a cos function, where the electric field is sine function. So E and I is always out of phase, but their direction is same, so therefore this option is not correct. Okay, now as we mentioned, B is equal to del cross A, then direction of B is must be perpendicular to the direction of A, so that is correct. So for this equation we are getting these two option is correct, A and C. With this all the question was done. So as I mentioned before closing it, I just explain something. This F H cut T I, that will, this thing is the main focus of this course, and it will be shown how H cut is in week 3 lecture. It will be demonstrate how H cut T will produce transition dipole moment. So transition dipole moment is actually determines how the transition from I to F is possible or not. If this value goes to the 0, this transition dipole moment, actually if you derive this, it will come like mu E I. So if a diatomic molecule AB diatomic polar molecule having permanent dipole moment is like this, and your electric field is going like that. This is a plus direction, this is a minus direction. Then in that condition, mu dot this is a direction of mu, and this is a direction of electric field. So if the molecule is aligned like this, then the mu dot E will be 0. So the molecule will not absorb any light. But if the molecule is aligned like this, like that, and any fashion, then this mu dot E is not 0. So dipole moment has a projection of the electric field. Therefore, this will give you some transition. So this transition transition moment integral will have a finite value, and this will be allowed transition, and this is forbidden transition. Now implication of this with different level of different spectroscopy method, absorptions, electronic excitation, rotational vibrational excitation is used in different books, and in the lecture also you will see that how it will be implicated. So with this I want to stop it here for this session, and if there is any doubt you can ask, and this is the all of this equation of the session. Okay. Levine, there is, I think it is written on your portal. So this Rabi oscillation thing is most probably coming from the Levine molecular spectroscopy, and there is few more else, Macholus, something like that. So basic thing is, so if you want to have this thing from the books like Banwell and all, you will not get. So this is some quantum flavor of molecular spectroscopy. So you will get in Levine quantum chemistry, or there is some book called Macholus. You can look at also. Okay, and it is also suggested in your portal. You can look at it. Otherwise, I will share it in. I will show it in the next class. Okay. Is there anything else? Okay. So with this, I am stopping it here. Save all these things. Okay. So